Welcome to the second part of second lecture. In the first part, we have learned about Eulerian graph. Now, we will talk about Hamiltonian graph. Again you recall that a path is a walk in which all the vertices are distinct, and once all the vertices are distinct, all the edges are also distinct. Now, a closed path is a cycle. So, a Hamiltonian cycle in a graph G is a cycle that includes all the vertices of the graph. And similarly, Hamiltonian path, a Hamiltonian path, also called spanning path, in a graph G is a path that includes all the vertices of the graph. And a graph is Hamiltonian if it includes if it contains a Hamiltonian cycle. So, this is the definition of Hamiltonian graph. Now, let me just give some example of graph. Say this is one graph with these vertices. Now, these two are adjacent. Now, the question is whether, let me call this graph as G1, whether this graph is Hamiltonian or not. So, you try to find a Hamiltonian cycle in this graph that you can try on your own. The question is whether G1 is Hamiltonian or it is not Hamiltonian. Let me draw another graph with 6 vertices. I am giving many examples so that the definition of Hamiltonian graph is clear to you. There is no doubt about the definition of Hamiltonian graph. Let me call this graph G2, and the third graph is this one. say G3. Okay. Now, if I label them A, B, C, D, E, F, I will talk about the graph G2 only. Can I find Eulerian, a Hamiltonian cycle here? Yes, probably I can find one. So, a Hamiltonian cycle in G2 could be A, then go to B, from B you go to C, and from C you go to F, and go to E, and then D, and then A again. I think I am not repeating any vertex here, and so it is a closed path. So, it is a cycle and it includes all the vertices of the graph. So, this is a Hamiltonian cycle. So, I can say that G2 is Hamiltonian graph. Okay. So, unlike Eulerian graphs, there is no known test or conditions that can be used to characterize or to determine if a given graph is Hamiltonian. Next, we talk about theorem. If G is a simple graph with n vertices and if degree of every vertex is greater than equal to n by 2 for each vertex B, then G is Hamiltonian. Okay. So, in the case of Eulerian graph, there is a characterization to characterize, there are some conditions to characterize Eulerian graph, like a graph is Eulerian if and only if every vertex is of even degree, but there is no such condition in case of Hamiltonian graph, and the theorem that I wrote just now is of course, it's an old theorem. It says that if G is a simple graph with n vertices, and if the degree of every vertex is greater than equal to n by 2, then the graph is Hamiltonian. One thing to note that this is not a necessary condition, this is a sufficient condition. So, proof of this theorem. So, the proof is by contradiction. This is by contradiction. Let G be such a counter example to the theorem, so that no graph on n vertices with more edges than G is also a counter example. Okay. So, let G be such a counter example to the theorem, so that no graphs on n vertices with more edges than G is also a counter example. Let U and V be two non-adjacent vertices of G. Okay, so you need to understand that this is probably the first non-trivial proof that we are giving. The proof is slightly difficult. The proof is using by the technique of contradiction. So, that means we suppose there is a graph G which satisfies graph G with n vertices. So, it satisfies the condition that every vertex has degree greater than equal to n by 2, but the graph is not Hamiltonian. And the counter example that we considered for this for the proof of this theorem is sort of a maximal counter example. That means, it has the maximum number of edges in the graph G. If you add one more edge to the graph G, then the graph become Hamiltonian. So, the graph the counter example that we considered is sort of a maximal counter example. Let U and V be two non-adjacent vertices of G, then there is a Hamiltonian path joining u and v in G. Because u and v are non adjacent. Now, if you add this edge u v in the graph, then the graph will become Hamiltonian. So, that means u and v these two vertices are joined by a spanning path or a Hamiltonian path. So, beside u and v there are n minus 1, n minus 2 vertices. Let me call them v 1, v 2, v k minus 1, v k, v n minus 2, because total number of vertices is n. So, n minus 1 vertices are here, sorry, n minus 2 vertices are here and then u and v. So, this is a spanning path joining u and v. Now, let the degree of u is equal to k, and we know that the degree of every vertex is greater than or equal to n by 2. Now, we prove that if u is adjacent to v k, then v k minus 1 cannot be adjacent to v. So, if u is adjacent to v k, then v k minus 1 can't be adjacent to v. So, this we prove just to determine the degree of v, and we will come to a contradiction. So, if u is adjacent to v k, then v can't be adjacent to v k minus 1, because okay, let me prove this one also. This is again by contradiction. If possible, let v be adjacent to v k minus 1. If this is adjacent to v k minus 1, then we have the Hamiltonian cycle v n minus 2 v k u v minus 1 sorry v 1 v 2 up to v k minus 1 and v. That means, if v is adjacent to v k minus 1, then we get this Hamiltonian cycle v n minus 1 v k, and then you go to u and then v 1 v 2 V k minus 1 and then you go to V. So, you get this Hamiltonian cycle here. Okay. Since we assumed that G is not Hamiltonian, G is not Hamiltonian, this is not possible. That means, see, we assume that G is a counter example. So, G is not Hamiltonian, but here it is becoming that G is Hamiltonian. So, that means V can't be adjacent to V k minus 1. So, V is not adjacent to V k minus 1, and you know that, see, U is adjacent to k vertices, and since U is adjacent to k vertices, V can't be adjacent to at least k many vertices. So, V is not adjacent to at least k vertices, k of the n minus 1 vertices. Thus, the degree of V. So, ultimate goal was to compute the degree of V and come to a contradiction. So, since V can't be adjacent to at least k of these n minus 1 vertices, you can see that the degree of V should be less than or equal to n minus 1 minus k, and k is greater than equal to n by 2. So, this is less than equal to n minus 1 minus n by 2. So, which is equal to n by 2 minus 1. So, thus what we got is that the degree of V is less than equal to n by 2 minus 1. So, this is a contradiction. Thus, G must be Hamiltonian. Okay. So, this is the end of this proof. So, we started with the contradiction that G is a maximal counter example to the theorem. That means, every vertex of the G has degree greater than equal to n by 2, but the graph is not Hamiltonian. And then finally, by after different steps, what we realized, observed that the degree of V is less than or equal to n by 2. Less than equal to n by 2 minus 1, which is a contradiction, because the original graph, in the original graph G, every vertex has degree greater than equal to n by 2. So, we came to a contradiction, and that is why the graph G must be Hamiltonian. That is all for today's class. Thank you very much.